Hello class, this is 8.1. Here we will learn about what is called sequences and partial sums. So we will begin with sequences. A sequence is a function whose domain is the natural numbers, or whose domain is the set 1, 2, 3, 4, and so on. Right, so for example, just say we have some function f. Say f is a function with domain 1, 2, 3, 4, etc. Then we can list out all of the outputs, right? And we can list out all the outputs, right? Or in other words, we can plug in 1 to the function, and that will equal some number. Let's call it a sub 1. That is a with a subscript of 1. We could plug in the number 2. That will spit out some other number, call it a2, a sub 2. We could plug in a 3. Right, and we can continue. If we plug in n, it will spit out a n, and so on. So intuitively, we can think of a sequence as a list of numbers. Think of a sequence as a list of numbers. And you've definitely seen a few sequences before. I will give you some examples. Consider the sequence given by the function where an equals 2n. And so we typically use this symbol for a sequence. Instead of writing f of n, when it's a sequence, we usually write it like this, an. But anyways, this function here, 2n, you've definitely seen the sequence before. If we start listing out the outputs, right, if we plug in a 1, a1 would be 2 times 1, which equals 2. a2 will be 2 times 2, which is 4. a3 is 2 times 3, 6, so on. So an is the sequence given by 2, 4, 6, 8, right? It's the even numbers. So even numbers are a sequence. So really what even numbers are the list of outputs of this function, 2n. And, a function with domain natural numbers is what the sequence is, but it's more intuitive to think of sequence as a list. This list of even numbers is the sequence given by 2n. Okay, another example is the odd numbers. The odd numbers are also a sequence. So the odd numbers are a sequence given by the formula. You could use 2n plus 1. Right? And if you just plug in a few values, you plug in a 1, you get 2 times 1 plus 1. It's 3. Let's use 2n minus 1, just so we don't skip an odd number. We could use this formula, but then we'd have to start at 0 instead of 1, but it doesn't matter that much. Let's use 2n minus 1. Then we plug in 1, we get 2 times 2 minus 1. 3. Oh, we still have to start at 0. 2 times 0. Oh, sorry. Sorry about that. Just kept making typos there. So I changed it to 2n minus 1. And then plug in the 1. We get 2 times 1 minus 1. Sorry about that typo. So that's 2 minus 1 equals 1. We plug in the 2. We get 2 times 2 minus 1. We make 4 minus 1. We get 3. Plug in a 3. 2 times 3 minus 1. 6 minus 1. 5. And so on. So the sequence is 1, 3, 5, 7, etc. The odd numbers. Okay, now that we're a little more familiar with sequences, let's look at a few homework problems. So let's be given a formula 5n minus 4. Let's find the first 3 terms and find a10. Okay, so the first term we just plug in a 1. It's as easy as that. 5 times 1 minus 4 equals 1. For the second term we plug in a 2. 5 times 2 minus 4. 10 minus 4. Third term, plug in a 3. 5 times 3 minus 4. 15 minus 4. Okay, so the first 3 terms right there. Now to find the 10th term, as you may have guessed, just plug in a 10. 50 minus 4. Okay, so hopefully it's making sense here. Let's look at another formula. Let's look at this one, negative 1 to the n times n. Let's just list out a few of this. Now, whenever we have a negative 1 to the n or something like this, we're going to get an alternating sequence. And what that means is one term will be negative, the next positive, the next negative, then a positive. And that's just how the powers of 1, that's how the powers of negative 1 behave, because negative 1 to an even will equal positive 1. Negative 1 raised to an odd number will equal negative 1. Right? Anyways, let's just plug in a few numbers, list out a few of the outputs. So if we plug in a number 1, we get negative 1 raised to the 1 times 1. Negative 1. We plug in a 2, we get negative 1 squared times 2. So the negative and the square cancel, we get 2. Plug in a 3, negative 1 cubed times 3, negative 3. And as you could see, you could sort of already see the pattern now. So we're going to get negative 1, positive 2, negative 3, positive 4, negative 5, positive 6. Right, we get this alternating sign because of this here. Okay, so if you're given a formula, it's pretty easy to list out some terms. You just simply plug in a number. But going the other way takes a little more cleverness. If you're just given a list of numbers and you need to find the formula, that's a little more tricky, and there's no general method that will work every time. You just have to be clever to do it. But if it's an easy list, then you don't have to be too clever. Like if we have, I don't know, just start out easy. Say we have the 1, 2, 3, 4, 5, etc. Right? find the general term an, right? So if we're given this really easy sequence, 1, 2, 3, 4, 5, if we're going to find the general term an, well, it doesn't take too much thought to realize we have an equals n, right? Just plug in a few values to this formula. Plug in a 1, you get a 1. Plug in a 2, you get a 2. Right, so this one works. Okay, what if we have this list, 10, 20, 30, 40, so on. So now we again want to find a general formula for this, right? Find a formula, find an. Well, we want to find formula that when we plug in 1, it spits out 10. When we plug in 2, it spits out 30. Plug out 3, it spits out. When we plug in 1, it spits out 10. When we plug in 2, it spits out 20. Plug in 3, it spits out 30. So it shouldn't take too much thought to realize these are all multiples of 10. So multiples of 10. 10n is in fact the formula, and you could plug in a few values to verify that this formula works. So again, when we have to reverse engineer a list into a formula, you just kind of have to think about it and then plug in some values to check if it works. Okay, and then once you do have a formula, you could find any term. Now that we have discussed sequences, let's move on now to sums. So a sum is a type of sequence. It's just when we add the terms of a sequence. So let's just look at an example first to begin our introduction on sums. So let's consider the sequence 2n plus 1. Okay, that's the sequence of odd numbers. What if we add the first 4 terms? Right, so to do that, we need to know what the first 4 terms are, right? So if we plug in a 1 to this, get 2, 1 plus 1, get 3. Plug in a 2, 5. Plug in a 3, 7. Plug in the 4, you get 9, right? Now if we add them, that's 3 plus 5 plus 7 plus 9. So I don't know, group those together. It's 8 plus 16. Right, and then we get 24. So the sum of the first 4 terms of this sequence equals 24. Now, if you notice, that was an easy thing to do, but look how much writing it took. So we need a more condensed symbol to do this, because this is a very common thing to do in mathematics, and we don't want to take up an entire page just to do something this basic. So what symbol we tend to use is the following. It's capital sigma. So we use a capital sigma, and then we put the sequence here that we were using in the sum. And now notice in the above sum, we started by plugging in a 1, and then we increment it up to 2, we increment it up to 3, and then we increment it up to 4, and then we stopped. So how we can represent that in the more compact symbols is we put the 4 on top, which means the fourth term is the last term we use in the sum. And since we started with plugging in a 1, we put a n equals 1 on the bottom. So this symbol just means exactly what we did above, but look how much nicer this looks than all of this, right? So to repeat myself, this n equals 1 on the bottom of this capital sigma means we start, or let me rephrase. This n equals 1 means that the first term in the sum is 2n plus 1 evaluated at n equals 1. Or maybe I won't use that symbol. Is 2, 1 plus 1, right? Then this 4 on the top means the last term in the sum is 2 times 4 plus 1. Right, and the reason we were plugging into 2n plus 1 is because we wrote that right there. Okay, so let me give you a few more examples now using this sigma notation. Right, so for example, say we want to sum the sequence g to the k, where we start plugging k in at 0 and we stop at 4. Well, that just means we start with plugging in a 0 for the first term of the sum, and we increment it up, plug in a 3, plug in a 4, and then we know to stop at 4 because that was the upper bound there. Okay, so that is the answer. Okay, let's look at some more sums maybe. Let's look at the sum -1 to the k times 3k, where k is from 0 to 2. So that means first we plug in a 0 for k, then we plug in a 1, then we plug in a 2, and we know to stop at number 2. Right, so -1 to the 0, that first term just equals 0, second term equals -3, third term equals 6, so we get 6 minus 3. Okay, so hopefully they're not too bad. Just try not to be thrown off by this new symbol, because all it means is just the sum. Okay, and the last thing I want to talk about is a recursive sequence. So, recursive sequence is a sequence where each term depends on one or more of the previous terms. So I'll give you an example. I'll give you two examples here. So for example, say the first term in the sequence is 0, the second term is 1. And then any general term is just the sum of the previous two terms. Right, so that means if we list out the sequence, we have 0, 1, the next term would be 0 plus 1, which equals 1. The next term would be 1 plus 1, which equals 2. The next term will be 1 plus 2, which equals 3. The next term will be 2 plus 3, which equals 5. Right, 8, 13, 21, etc. Okay, now this is actually a famous sequence. It's called the Fibonacci sequence. A few cool things about it. If you draw squares whose area equals these numbers, and you stack up the squares in this way, they make a spiral, and it happens to be a spiral we see in nature a lot. You see it in seashells, pineapples, and your fingerprint. The galaxy is sort of shaped like that. The way trees branch out to maximize the sunlight they get sort of follows these Fibonacci numbers. See them in population growth, stuff like that. So pretty interesting applications. Let's look at another recursive sequence. I believe you may see similar ones in your homework. Say the first term in a sequence is 2, and then any term will equal 1 plus 1 over the previous term. Alright, so if you're a little confused about that, just start plugging in numbers. Say we want to find what A2 equals. Right, well, A2 by the above formula would be 1 plus 1 over A1. And we know what A1 is because we were given A1. So that equals 1 plus 1 half, 3 halves. A3, therefore, will be 1 plus 1 over A2 by the formula. So 1 plus 1 over 3 halves. 1 plus 2 thirds. 3 thirds plus 2 thirds. 5 thirds. Then A4 would be 1 plus 1 over A3. So 1 plus 1 over 5 thirds. 1 plus 3 over 5. It's 5 over 5 plus 3 over 5. Right, and you could just keep doing that. So that is a recursive sequence. It's just when you use one of the previous terms in the next term. Okay, and with that, we will end today's lesson on sequences and sums. And this is the last of the material we will go over for this semester. So thank you all for learning. Okay, have a good day.